So when we have a look at the syllabus, we're still looking at the focus question, how does training affect performance? But we've moved down a dot point and we're now having a look at physiological adaptations in response to training. So these are things like heart rate, stroke volume and cardiac output, oxygen uptake and lung capacity, hemoglobin level, muscle hypertrophy, and the effect on fast, slow twitch fibre muscles. Now, some of these things you would have seen in the preliminary course, so we probably shouldn't have to go too in-depth with these because you should already have background knowledge of these concepts. So we start by having a look at heart rate, or HR, and how does our heart rate change because of training. So throughout the video, we're going to look at two concepts of looking at the adaptations to the body at rest and the adaptations during exercise. Now, some of these things will be the same for at rest and same for during, but some will be a little bit different. So when we have a look at the heart rate, the adaptations at rest is that our heart rate will decrease. So it'll be a lower heart rate at rest when we're more fit or we've been training than what it is if we haven't been training. During exercise, we're going to have a lower heart rate at all intensities. So obviously the fitter we are, the more we're training, the lower our heart rate. And the reason for both of this is that there's an increased stroke volume which allows for an improved efficiency of the cardiovascular system. So when we talk about stroke volume, we're talking about the volume of blood pumped around the body in one beat. So the more training we do, the more we train our aerobic system, the more blood we can get pumped from our heart to the rest of the body per beat. So obviously, if we're having more blood being pumped out per beat, the heart isn't having to pump as fast. So the more training we do, the less beats per minute our heart pumps to get blood around the body. So then obviously from our heart rate, we continue on to stroke volume, or SV. So as we said before, stroke volume is the volume of blood which is pumped around the body in one heartbeat. Now, what does it look like when we apply training? How does our stroke volume change? Well, at rest, it increases, and obviously during activity, it increases. So back to that principle when we're talking about heart rate, the volume, obviously, the more we train, the more blood we can pump out through our body. And the same reasonings for this, for at rest and during activity. So the left ventricle in the heart increases in size and the strength of contraction of the left ventricle increases. Now, because of those size increases and the strength increases, the left ventricle is able to fill more completely during the diastole phase, and that allows for more blood in circulation. So basically, an increase in the left ventricle in size and strength allows for more blood to be pumped around the body, which increases our stroke volume at rest and during exercise. The next physiological adaptation we look at is cardiac output, or CO. Now, cardiac output is the amount of blood pumped around the body in 1 minute. It is a product of stroke volume and heart rate. So when we look at our output altogether, we calculate how much blood is circulating in our body over a minute. Now, when we look at how this is affected at rest and during exercise, at rest, our cardiac output remains relatively unchanged. So when we're sort of sitting there, not really doing anything, the cardiac output remains the same. During exercise, it's obviously slightly decreased, and this is because our heart rate decreases as a result of training. Obviously, there's going to be a slight increase in the cardiac output when the intensity reaches the maximum because our body is trying to pump as much blood as we can, and our heart rate's increasing, and so is our stroke volume, so therefore our cardiac output's going to increase. Now, when we have a look at why our cardiac output remains relatively unchanged at rest, it's due to the fact that the stroke volume has increased, and obviously the heart rate decreases accordingly to that. So it sort of kind of weighs out a bit. Now, you've got to remember that with cardiac output, it is the equation of our heart rate times our stroke volume. So as soon as we know what our heart rate is and we know what our stroke volume is, we can work out our cardiac output, and we can work out how much blood is actually pumping around the body per minute. So when we have a look at why we have this slight decrease in our cardiac output in training, it's due to the fact that we've got that increased stroke volume. So during exercise, our cardiac output can be very high due to a high heart rate and a high stroke volume. Now that's when we're at that high intensity level max. That's not when we're just training in our aerobic threshold or just below our anaerobic threshold. That's when we're really pushing the limits, when our heart rate has increased considerably and our stroke volumes increased considerably. That's when we're going to see a really big rise in our cardiac output. But generally it sort of remains the same or decreases a little bit during exercise if an athlete is training. The next thing we look at is the oxygen uptake. Now, the oxygen uptake is the body's capacity to absorb and utilise oxygen in 1 minute. So, over a minute of time, how can we actually take on how much oxygen can we take on, and how much can we actually get out to our muscles in time to be able to create more energy. Now, when we have a look at oxygen at rest, or our oxygen uptake at rest, it's obviously increased when we apply training, and the same for during training, it increases as well. Now, when we have a look at the reasons why for this, it's because the number of oxidative enzymes have increased, and therefore the number and size of mitochondria also increased. Now, when we talk about this concept of oxidative enzymes, these are enzymes that exist in breaking down chemical compounds. For example, the breaking down of carbohydrates and fat to produce ATP. Now, the more oxidative enzymes can mean that the athlete has a greater capacity to utilise carbohydrates and fats to produce energy aerobically. So obviously, if we can increase our oxygen uptake, this means that we can increase the amount of these oxidative enzymes, which means that we have a better capacity to break down carbohydrates, fats and proteins for energy. Now, having a look at what is mitochondria, mitochondria are the organs that are found in large numbers in most cells, and it's up to the mitochondria to process respiration and energy production to occur. So obviously, if we can have more mitochondria in our muscle cells, that means that we can have more energy that can be created by the increase of oxygen in our muscles. And then finally, we look at the concept of the fact that because our stroke volume is increasing, that means that our blood volume around our body is increasing, which means that we can actually get more oxygen into the blood system, which is obviously going to allow for this increased amount of oxygen because we've got an increased amount of blood. So the next part of the dot point we look at is lung capacity. Now, lung capacity is the volume of air in the lung as a result of maximal inspiration. So basically, the amount of air that we can hold in our lungs when we breathe in. And we take oxygen in, how much air can we actually hold in our lungs? So when we have a look at how is lung capacity affected with an increase of training at rest, we see a little change in relation to lung capacity. During, we see little change as well, but obviously, again, this may increase at maximum exercise. Now, remember, maximum exercise is when we're really pushing the limits. It's like when we're tapping past our anaerobic threshold and our body's really sort of sucking in for air, okay? Now, when we look at the little change at rest, it's due to the fact that we've got an increased blood volume and therefore more red blood cells that is getting oxygen around the body. So the lung capacity is not necessarily going to change too much. It's more about the capacity of the blood cells in the body. And that's the same as well for during activity. Because we've got an increased amount of blood cells or blood volume, we've got more red blood cells in the body which can carry oxygen. All right, the next physiological adaptation we look at is the hemoglobin level. Now, Hemoglobin, big word, what does it mean? Basically, hemoglobin level is the amount present of the protein part of the red blood cell, which is called hemoglobin. So when we look at our red blood cells, the protein part of it is hemoglobin. So hemoglobin is a molecule capable of being combined with oxygen for transportation around the body. So when we look at our red blood cells and they're being transported around the body, hemoglobin attaches to the oxygen in the red blood cell and then sends that out to the muscle cells, and then we know that once we have oxygen in our muscle cells, we can start breaking down lactic acid from the lactic acid system, and we can start creating ATP again. We also know that oxygen, once we start to sort of use the ATP sources up through the lactic acid system, we can then get blood to other areas of our body where we can help break down carbohydrates, fats and proteins with the hemoglobin, because it's carrying the oxygen to provide us with ATP as well. So when we look at how does hemoglobin levels, how are they affected with training? When we look at rest and during exercise, our hemoglobin levels are increased the more we train. And this is due to a growth in size of the muscle fibers. So obviously the more muscles we have, the more blood and the more hemoglobin that is traveling around our body, because blood circulates to working muscles to provide the muscles with oxygen, to provide with energy. Now, when we look at during training, it's increased. One of the reasons is because the muscle growth occurs during rest and recovery phases after exercise, okay? So obviously we continue to increase the hemoglobin levels during exercise, but that level can remain the same, and if not increase after exercise, because we need oxygen to go back to our muscles to repair and replenish oxygen stores. And this is why our hemoglobin levels are increased at both at rest and during exercise. The next aspect we have a look at is muscle hypertrophy. Now, what is this big word? Basically, hypertrophy means an increase in the size of muscle fibers. So can we get our muscles bigger, basically? And it's usually in response to strength, sort of resistance training. And there's a higher correlation between muscle hypertrophy and muscular strength. So basically, the bigger your muscle is, the stronger your muscle is going to be. So when we have a look at applying, say, resistance training to an athlete, how is their muscle hypertrophy affected? So we look at rest, it's obviously increased, and during, it sort of stays unchanged. And let's have a look at why it stays unchanged or why it increased. So when we're at rest, the growth in size and function of the muscle fibers is being able to be repaired, and there's an increased capacity to contract strongly and or for longer periods of time. So when we actually work out during training, we're obviously training our muscles to be more sufficient, but in relation to our muscles actually growing, this happens in the rest stage when the muscles are actually repairing, and we're using proteins to repair and help grow the muscles. That actually happens outside of the activity. Now, obviously, during activity, it's very much not a case of that the muscles are growing. They're sort of staying the same size. And this is due to the growth in size of fast or slow twitch muscle fibers, and the fact that the enhanced function and growth occurs during rest and recovery phase after exercise rather than during the phase of exercise. So the final adaptation we have a look at is the changes to fast or slow twitch fibers. Now, fast twitch fibers are present in muscles and are capable of strong and fast contractions over short periods of time. So you might hear a statement every now and then that, oh, so-and-so is built for sprinting because they've got fast twitch muscle fibers, or, you know, they're designed to be a marathon runner because they've got slower twitch muscle fibers. So this is where this concept comes from. So when we link back to our energy systems, back at the start of core 2, if we have a look at fast twitch fibers, they're muscles that are sort of moving and doing movements really quickly. So they're using ATP-PC system, sometimes the lactic system, and therefore do not need to use oxygen to generate fuel for contractions. Now, slow twitch fibers contract less powerfully and more slowly, but are able contracting for longer periods of time, and this is because they use oxygen. So they're using the aerobic energy system to generate fuel to contract. Now, going back to what I said with the start of this part of the video, is that the proportion of fast and slow twitch fibers that are present in a person's muscles can obviously influence their natural talent or their natural ability for a certain sport. So obviously, if an athlete has fast twitch fibers, genetically, they're going to be suited to sports which are more powerful, which require a lot more speed. If they've got those slower twitch muscles, they're going to be more suited to endurance sports. So let's start to have a look at how our fast and slow twitch fibers are affected as a result of training. So at rest, the size and function of our fast and slow twitch fibers increase. And during, the strength and repetition of the contraction increases. So going back to what we were talking about before about muscle hypertrophy, is that a lot of muscle growth and development happens during rest when our body is putting protein back into the muscles for growth and repair. So growth and repair happens following a training session. So therefore, that's why at rest, we have an increase in size and function of these fibers. Now, during it, we have an increase of strength and repetition of contractions, or our ability to contract our muscle either faster or for longer. And this is due to the increased size of fibers that have happened at rest from a previous session, and also, which is important to note, an increase of aerobic function. So the more aerobically fit we are, the longer we can perform, and therefore the more contractions we can do, or actually the size of the contraction that we can do. Now, remember that this video is just having a look at the learn about side of the syllabus. So you're learning about heart rate, stroke volume, cardiac output, oxygen uptake, lung capacity, hemoglobin level, muscle hypertrophy, and slow twitch or fast twitch fibers. What you need to actually be able to do is the learn to side of it, and you need to have a look at the relationships between these physiological adaptations. So, for example, the relationship between heart rate, stroke volume, and cardiac output, or even between muscular strength and muscular hypertrophy. So these are sort of things that you'll need to discuss in class with your teachers, or further study yourself through some practice questions.